Very well. So very happy to have Hector and Freitas from Cycling for the second talk, and it's going to tell us about the supersymmetric vacua dimensions.
Well, first of all, thank you very much for the invitation to speak here. We're happy about this. And yes, the topic of this talk is what the title says, new supersymmetry strings in high dimensions. So let me start with the motivation for this problem. There is a basic problem in string theory that is to chart the landscape of string vacua. And you can do this kind of thing relatively easily when the amount of supersymmetry is very high. So in particular, with high maximum supersymmetry, which corresponds to 16 supercharges, you would expect that you could find some complete picture here. Now, why is this useful? Recently, there has been some progress in the Swampland program, which aims to understand what are the constraints that you have to put on EFTs in order for them to be consistently coupled to gravity. And for this, in principle, since you have a theory of quantum gravity, which is string theory, it would be good to know what is actually allowed there. And so you can test any conjecture that you have.
So you can fake the answers better.
Well, I have no opinion on this. This problem is very old. I mean, this was studied very exhaustively 20 years ago in the regime of 7 dimensions and higher, where this is the minimal supersymmetry. It was almost solved. So in this paper of the Bohr and company from 2001, what they did was they constructed many string vacua using heterotic strings, type 2 strings, theory, and different settings. All of them, of course, restricted to having 16 supercharges. I mean, you don't want to break supersymmetry more than that. And what I want to show is that from their analysis, if you do things a bit more carefully, you will see that there are missing components in the moduli space. So the picture here is that you have a moduli space of string vacua. It has many disconnected components, and you can encode them using so-called frozen singularities, as I will explain. And if you use this, you can find some new theories, and they are described with discrete angles, which will be the second part of the talk. So the outline for this talk would be, I will first explain what is known about moduli spaces so far in this regime of 16 supercharges and high dimensions. Then I will explain what is this frozen singularity business on K3 manifold, this is some theory. And then we will see how we can predict new components of the moduli space, and then I will try to explain to you how they're actually realized using string theoretical constructions, and then some conclusions and some open problems. Okay, so perhaps the easiest way to get into this is from the heterotic string picture. If you are in 10 dimensions, you know that you have 5 superstrings, and 3 of them have 16 supercharges. Which are the 2 heterotics and the type 1. If you take these theories, and we'll focus on the heterotic for simplicity, if you take these theories and you compactify on a torus, you will not break supersymmetry. And the theory that you get has moduli, which give rise to a modular space of this form in general. So this is just some torus, some D torus. And the front of the modular space is like this. So you have, if you ignore the first term, you have some factor, which is a symmetric space, which tells you about the local geometry of this moduli space. And then you quotient this by some discrete group, which is the automorphism group of some lattice. Okay, this is fine.
We don't read too long.
Okay. And then there is this dilaton part, which is not relevant for what I will be talking about. So in the case of the heterosis string, how this is realized, the moduli are internal components of the metric of the two-form field, the B field, and Wilson lines. And this lattice, which is very important for the analysis that we will do, it tells you about the winding number of the strings as they grab on this torus, the quantized momentum that they have charged with respect to the gauge lattice. So the heterotic strings, recall that they have some gauge symmetry, and these are associated to some events of dual lattices. So the strings will also have charge with respect to that. So this is the simplest moduli space, or the most important moduli space. It's called the Narain moduli space that you have from this series in different settings. You can construct other moduli space. On the compactification circle. So the setting that you're looking for, you have a transformation that when you go around half of the one of the compact circles, the two E8s will switch. If you do this orbifold, you will get a theory that has a rank reduction. So here you see that the model space is O, D, D plus 16. That D plus 16 tells you about the rank of the gauge groups that you can realize in this theory. And here that number is reduced by 8. So the moduli space generically has a smaller dimension, it's simpler in some sense, but it exhibits other interesting properties, though they will not be relevant for the analysis. Here, interestingly, the lattice, the so-called Narain lattice, is even and self-dual. This is required from modular invariance of the theory. But when you start doing these orbifolds and you get rank reductions, this will not necessarily be the case. This a generic property. So it's an observation that we can. So here we have two string theories that live in different moduli spaces. They actually live in different moduli spaces. And this theory you can construct in 9 dimensions. You only need a circle. When you go down to 7 dimensions, the lattices that you have, the theories that you have other symmetries that you can use to construct other orbifolds that will preserve supersymmetry. And these are called heterotic holonomy triples that were constructed in this paper that I was referencing. And the C-shell string that I talk about is, just think of it as an orbifold of order 2, but here we can follow that sequence 3, 4, 5, and 6. You can do this with heterotic strings. So all in all, so far we have 6 different moduli spaces, and they are all of this form. So I would just comment that because of the supersymmetry, the amount of supersymmetry, every moduli space that you have will generically have a form like this. In this case, we just see a change in this, basically in the
My last value is 18.
Yes, yes, you're right. No, wait. No, it's 16. It's 16 because this is heterotic string only. So I'm referring to 6 different components, and these are 6 numbers, and 2 of those components have the same rank. Okay. Right.
That's truly the same moduli space, and in fact they are equivalent.
No, they are not equivalent. They are 2 different.
Yeah.
The rank reduction is the same, but the 2 moduli spaces are different. This is a very interesting question. So one thing that you can see that is different is that the level of the gauge algebras that arise there are different. So, and the order of the orbifolds are different. 5 and 6, but they turn out to have the same rank. Now you can compute this lattice here, which is not even self-dual, it's some lattice you don't know a priori what it is. But when you compute it, you see that it is actually embedded in the Narain lattice of the original modular space. So it's a sublattice of that. Is there?
You can continue.
Okay, so if you.
Sorry, I am a bit confused.
Yes.
I thought if you have an even lattice and the signature is modic, it's unimodular.
No, this is not true. It's not.
Not necessarily. Is that necessary repetition? No. It's necessary but not sufficient. Yeah, so this is what.
Yes, exactly.
Most lattice development.
Sorry?
Most given lattice development.
Yes, even and signature A.
It's anything not enough. Not but
It can be scaled by any factor.
Yes, exactly. Now, interestingly, if you then can compute what is the orthogonal complement of the lattice when you embed it into the Narayan lattice, and you get this sequence. So for what is the CHL string, you have a 2D4 lattice. These are root lattices, and so on. So this will be important for what we will do. So far we have 6 moduli spaces. When you're in 7 dimensions, they have a dual picture in terms of F theory. Now you can take F theory and compactify it on a manifold of this form. So this is a K3 surface times a circle, and you quotient it by a symmetry of the K3 together with a shift on the circle that has the required order. So this is an orbifold, and it's fine. You get a field with 16 supercharges. But if you are in F theory, there are more things that you can do. You can get 4 more components that are described instead of a K3. You have basically a T4, and now this orbifold will break the supersymmetry because a T4 will preserve your supercharges. So recall that F theory is based on type 2B, which has 32 supercharges. So with this orbifold, you break it down to 16, and you get 4 more components that you cannot describe using heterotic strings. And the associated rank reductions, I just comment that one of these, which has disorder to orbifold, it's dual to a type 2A orientifold. I will describe it in a moment. And if you look at the rank reductions, now you have 16, and you have 3 of them that have rank reduction 18. These are the ones that have rank 1, 19 minus 18 is rank 1 gauge symmetries. And again, you can ask, are the lattices, the charge lattice analog to the Narayan lattice, embedded into the Narayan lattice? The answer is yes, and you compute the orthogonal complements, and you get these lattices. Now, I say here that they are roughly the orthogonal complements because these are not all of them root lattices. They have other vectors, and they will play an important role. But the root sublattices are of this form. So you can see maybe from here that you have some D4 factors, E6, E7, E8, and here again different combinations of these things. And so, well, this is what will turn out to be this will help us understand the frozen singularity picture. But before that, I just want to mention that of these theories, some of them, well, you can decompactify them, preserving the structure. So here, this is just the 2D4. I'm thinking here about the orthogonal complements of the lattice as something that is characterizing these theories. So the 2D4 corresponds to the CHO string, the one that has rank reduction by 8. If you go to 8 dimensions, if you decompactify the thing, the lattices change in such a way that when you again embed one into the other and compute the orthogonal complement, it's now D8, so it grows. And if you go to 9 dimensions, the relevant lattice will be E8, and this is for the CHL string. As I said, there is this n equal 2 orbifold. It also uplifts way to dimensions and to 9 dimensions. Here, interestingly, when you go from 8 dimensions to 9 dimensions, it splits. So it's a similar picture to the heterotic strings. Now, you may want to recall that the heterotic strings, when they're in 10 dimensions, there are different theories, but when you compactify them on a circle, they now form part of the same moduli space. They're equivalent. So it's a similar thing happening here. You have 2 theories in 9 dimensions. When you compactify them on a circle, they become equivalent. So this is the kind of picture. And if you want to know how they are realized in 9 dimensions, you can take one to be M theory in a Klein bottle, and the other to be the so-called type 1 prime theory with 2 orientifold planes that have opposite charges. Okay, so it's just the dual of type 1 on a circle. with an orientifold plane with positive charge. The point that I want to make here is that, sorry, the other modular spaces, they live in 7 dimensions, you cannot uplift them. But the point that I want to make is that if you look at the 4D4, in this case in particular, there is an equivalent way to have a 4D4. So there is a pattern that if you look for lattices that have the form of 4D4, there is another one that is an equivalent. And there is a natural pattern distinct uplifts to an equivalent 2D8 and an equivalent D16 in 9 dimensions. And this suggests that there is another component of the modular space in 9 dimensions, right? So one of the goals will be to understand this.
So, sorry, when you said the other live in 7 dimensions, you can assume locally the symmetric space is always of 3 something.
Yes.
And so you can always have you have at least those three, so you can always have.
You can decompactify the thing. You can decompactify the thing, but it will give you, it will take you back to the narrow modular space. So you will remove rank.
It's not interesting because we go straight to maximum.
Yes. So that rank reduction doesn't exist in 8 dimensions. But in 7 dimensions, it's also the case that you can find alternative versions for some of these theories that are characterized by these lattices. Okay. So this is the picture of what is known. So basically, you have 10 theories that are known in 7 dimensions, and 2 of them,
I'm a bit confused.
Yes.
About your nomenclature.
Yes.
What you label in any dimension is the reduced group, right? The part that you kind of group.
Do you mean what I'm trying to say by 2D4, D8, and so on?
Just like, what does 2E8 stand for? So you are going from rank 18 down to rank 2.
Yes.
In 8 dimensions.
By 2E8, I mean that if you take the charge lattice of the rank reduced theory and you embed it into the Narayan lattice, the orthogonal complement will be 2E8. So saying 2E8 is equivalent to saying what is a charge lattice. But the patterns are easier to see in the orthogonal complements, and they have a natural interpretation in terms of singularities of a K-tree manifold. So let's explain what are these frozen singularities. So a brief review. If you take M theory and you put it on a K-tree surface, this thing is dual to the heterotic string on T3. So it's a 7-dimensional, it gives you a 7-dimensional vacuum with 16 supercharges. The nice thing about this theory is that the moduli space is just the moduli space of K-tree manifolds, because M theory has a metric, it has a tree form, but you cannot get moduli with the tree form because a K-tree doesn't have 3 cycles. So, and this is the same modular space as the Narayan modular space. This is a way to match the 2 theories. But here, the gamma 319 is interpreted geometrically. It's the middle cohomology lattice of the K-tree manifold. So the moduli space, this is the moduli space of complex structures, is just telling you how you are deforming this K-tree. How you are deforming the complex structures is polarizing the lattice. So if you look at the moduli space and you are in the bulk, let's say a generic point, the K-tree manifold is smooth, but when you go to the boundaries, this manifold will develop AD singularities. And these are important because these AD singularities tell you about the gauge symmetries that your vacua have. So if you have certain collections of singularities in the same paper that I have been talking about from the beginning, given that they had these patterns in heterotic strings and M theory, they propose, okay, there should be a way to obtain these things from M theory, but in M theory, I only have the K-tree manifold, which is defined by the metric, and I have a tree-form field. So the tree-form field should be involved in this M theoretical picture if I want to get the other moduli spaces. So what they said was that, okay, you can turn on the tree-form field in some specific ways when you have certain ADE singularities, such that these singularities will become frozen. Here is where I want to make the contact with the lattice picture, because the cohomology lattice is telling you about the middle cohomology is telling you about two cycles, it's giving you information about the singularities. So the sublattices that I was talking about, which are the orthogonal complements of the charge lattices, they correspond to these process singularities. So, for example, if you have an AD singularity of type B4 and you have another one, you can turn on the three-form field in some way such that they will become frozen. Frozen means that you cannot resolve them. So the moduli that are associated to the resolution, they are frozen. And this corresponds to a reduction in the rank in the dimension of the moduli space. Now, this operation is discrete. You turn this thing on, and the three-form field will have some discrete values. And this discrete operation will define another moduli space. The remarkable thing for me is that with these nice rules, you encode everything that you know. So you have a kind a bookkeeping device for keeping track of the different moduli spaces. If you treat this problem more carefully, you actually see that you predict more. So to get some intuition for this, maybe a more familiar picture, if you take a type 2A oriented in 7 dimensions. So you just take your type 2A string, you put it on a torus, and you quotient by some operations, some reflections on the torus, and you get a cube. So you have 8 orientifold planes at the vertices of this cube. We show some pictures in a moment. And you have 32 D6 branes in order to cancel the tadpole. If you have a stack of an orientifold plane with 8 D6 branes, we know that you get an SO8 group and or algebra, and this thing leads to a D4 singularity when you go to M theory on a K3. This number, because M theory on a K3 is giving you a non-perturbative description of this setting. If you take 2 of these stacks, you can trade them, each one of them, for now an O6 plus plane. Why can you do this geometrically? Well, because this stack and these O6 planes have the same charge, the same brane charge, and they have the same tension. And now this thing that you have in type 2A, you lift it to the frozen singularity. This is a nice way of understanding why you lose moduli, because if you have an O6 plane, you cannot take out the branes. You lose that freedom.
How do we see 3-4? I mean, you still don't have a 3 cycle.
No, you don't have a 3 cycle. So the 3 form is not giving you moduli. You are just turning on the 3 form in some specific way, such that when you integrate it in a 3 sphere bounding the singularity, it gives you some integral value. So it's just some non-trivial background. It's not associated to the moduli. But this picture is not actually well understood. This is something that you argue that should be the case by using dualities. So the details of how this actually works.
Think of net connection with non-trivial.
So you need so the 3 cycle is what, the length space at infinity, the AE, or what? This S3, which is that?
No, the S3 is not a non-trivial cycle. It's just it's like you are computing some kind of flux or Wilson. So it's the integral of C3 is a 3 form to integrate it. Sphere. It's like a flux.
Yes. So probably
yeah, if you model it locally, then this will be the picture. You take the singularity to be some ALE space, and then the 3 form should be such that you get some value when you integrate it. But yes, I didn't want to go into the details here for that. But essentially, these rules are derived from duality. So yes.
Is it true to say that there's no geometric picture of these orbifolds from N series, or that there are these orbifolds that don't?
Yeah. They don't have a geometric description. If you go to 6 dimensions, then there is a geometric description available. because with that cycle, the new circle, you can do orbit folds of the kind I explained. But in 7 dimensions, it's all non-geometric. However, what is true is that the F theory picture is geometric. So what is non-geometric here actually maps to a geometric picture in theory. Here, when we freeze the 2D4, the resulting moduli space that you get is this one. It's rank reduction by F. So it's rank 11. But you can also trade 4 of these stacks. And you have a rank reduction of 16. You have this moduli space here. So the general picture of this frozen singularity business is that you can have frozen singularities of type E4, E6, E7, and E8. And there are only some consistent combinations. They have to do with the values of the tree form when you integrate them. And you play a certain game and you end up with these configurations and they match exactly what you had before. What you knew you should have from the dual frames. So there are these ones, but the key point is that the K-tree manifold. So in order to freeze the singularities, the K-tree manifold has to have them. So you have to be in some region of the moduli space where the K-tree manifold has developed these ADA singularities. The main point of this whole thing is that the 4D4, 3E6, and 2E7 plus D4, those configurations can come in 2 inequivalent ways. So you can have your K-tree develop the singularities in some way and in a different way. And we will see how this shows up in terms of lattices. And they will give rise to different moduli spaces. They need to. So how do you see this? Yes.
So when you trade 2 of the D6 to form a 4-6 plus,
yes,
you have chance to see USB6.
Yes, the gauge symmetry that you will have then, if you put more brains on that stack, is SP.
From this, can you see this algebra?
From the point of view of M theory, yes, you can. There is a whole story of how you get gauge symmetries from the lattices, and all of this matches perfectly. So, in the case that you mentioned of SP, you would look into the CHL string because, well, this is the CHL string. You trade, you have a frozen 2D4, let's say. When you do that, you can see what is, you can have a, how to explain. So you can start with a stack that has more brains, and this will correspond to a polarization of your lattice. And then when you freeze the singularity, this is more like a partially frozen singularity. You can see how the lattice changes, and you can see explicitly how the lattice of the weight lattice of some orthogonal group will correspond to the weight lattice of some symplectic group. So this is something that you can replace. Okay. Now, to see more precisely why these AD singularities can come in equivalent ways, we have to see where they are encoded. They are encoded, as I mentioned before, in the middle cohomology lattice. How precisely as Euclidean sublattices W? So Euclidean sublattices, you can do a classification of what are all the possible Euclidean sublattices that will correspond to symmetry enhancements. And I did this with Donaldo Freiman last year. We looked at the heterotic string, but the thing is dual to M theorem of K3, so they're exactly the same results. So we have a complete classification of how the K3 can develop singularities. To be more precise, if you want to see the AD type of the singularities, you look at this lattice and you look at the roots in that lattice. So you look at the root sublattice, it will have an AD type, which corresponds to your singularity. But the main problem is that this lattice doesn't necessarily have only roots. It can have other vectors that will make it different from others that have the same root sublattices. In the language of gauge, the language of group theory, you can think of them as fundamental weights. Indeed, they will correspond as to fundamental weights in the gauge group. So to give an example, a simple example, you can take the lattice that corresponds to spin 32 mod set 2. Spin 32 mod set 2 is the group that you put in 10 dimensions from one of the heterotic strings, and this is embedded into the lattice. So it means that there is a configuration of the K tree where you will see a D16 singularity, but there is another lattice that also has a D16. This time the associated group is a spin 32, which is simply connected. It's different. So they share the D16, and the difference is that the first example has elements in the spinor class of spin 32. The other only has roots.
But you have elements in the two spinor classes as well.
If you put elements in the two spinor classes, then you don't get an even lattice, because then you can.
You want to preserve it.
Spin 32 for me, I don't understand what is the distinction for me. Well, in the first case, we say that because there is the weight of the spinor representation, which is norm 4. But here, if you have spin 32, what do you mean that if you have the vector, it would be norm 1, which is not very even?
Yeah, it's tricky because spin 32, you have to think of this in the context that the spin 32 lattice, the root lattice is embedded into this other bigger lattice. So the representations that are associated to this group are not actually in the root lattice. So to be more precise, perhaps, the statement is that if you have this this configuration, which corresponds to a spin 32 lattice, then in the full lattice you will have states that are charged in the two representations of in the two spinors, but also in vectors. So it's
That's what I meant. The spinor is norm square 4, which is fine. But
yes, but
don't see how to add it.
yes, but the spinors they are allowed if they are not actually in the spin 32 lattice. They have a leg in the spin 32, but they also have a leg in the orthogonal complement, and they can be light like these vectors don't.
This is what you mean by spin 32.
Yes. So okay, maybe it's more fair to say that this is the root lattice spin 32. But the fact is that this is the cache group that you have.
Because you have massive state in the vector representation.
This is also true. Yes. In particular, the set 2 in the spin 32 that spinor is massive. So for us, what is relevant is that this combination 44 that I was talking about, it has the one that is known, it corresponds to a lattice that is of this form. So is the lattice of spin 8 and it has a fundamental group that is set 2 times set 2. This is also related to massive states. So if you want to find this is the lattice that is associated to the configuration that you can freeze in order to obtain the known theory. So here we have the type 2A fixture. This is the orientifold, and I traded for stacks of 6 nines and D brains. So these are the 4 positive couplings, and the other side you have the negative ones. So there is a correspondence between these two things. And when you do the freezing, then the fact is that the lattice that you get the charge lattice. Here I'm talking about M theory, so this is charges of M2 brains wrapping in cycles. If you take the orthogonal complement of this lattice, you get the charge lattice, which is this one. Now a bit of notation here. This gamma 1,1 is the even lattice of rank signature 1,1. So it's a hyperbolic lattice, and when I put a 2 like this in parentheses, it means that the lattice is scaled by a factor of 2 in the metric. But what I want to highlight is that there is another configuration where the value corresponds to a different lattice. Now, in the fundamental group of the gauge group or in the configuration of the lattice, now you only have one set 2. It means that there are less fundamental weights in that lattice. It also has an embedding into gamma 19, and you should be allowed to freeze the singularities. we play the same game, we take the orthogonal complement and find that we have this different charge lattice. So you see a difference at the level of the charge lattice. This will tell you that there is a difference in the spectrum. Now, how do you realize this using the orientical picture? You can do this by trading one orientical plane with another with the opposite charge. So these two configurations were detected in the paper of the Boer et al. In 2001. At the perturbative level, they said these things are inequivalent. We don't know that inequivalent non-perturbatively. So the answer to that problem is finding the correct embeddings, which are these ones. So that problem is solved in this sense.
There's a third possibility of choosing the assignment of O plus and minus on the cube, right?
Sorry?
Isn't there a third possibility of choosing the assignment of plus and minus on the cube?
In principle, you can try to play this game, but you will see that what you get is equivalent to something that you already have. To be honest, I don't know how to detect this inequivalence from the point of view of the orientals, but you can see this kind of thing from the point of view of the dual heterotic string, but it's a detailed process that I don't want to get into. But yeah, the moral of the story is that you have this a priori inequivalence that is lifted non-perturbatively to M theory. So to highlight some difference between these two moduli spaces, you can ask what are the gauge symmetries that you can realize. As I said, there is a way to detect these gauge symmetries using the lattices, and we see that there is only one point of maximal enhancement. So you generally have this your moduli space, and at some points you have bigger gauge symmetries. The difference between these two is at the level of the topology. You can see that both maximal enhancements are SU2 cubed, but the fundamental groups are different. And the difference in fundamental groups for theories like this, you see it at the level of massive states. So the topological gauge group is different. This is due to massive states being different. And then we can do the same thing for the other two singularities that I talked about, these configurations 3.6 and 2.7 plus D4. And here on the left hand side, I have the original lattices, the known components, and these are the alternative versions. So an interesting thing to see is that the difference between them is always a scaling of some factor in the lattice. So in the case of the 44 configuration, when you take the alternative one, you will scale the first lattice. Now, scaling this lattice just means that one of the quantum numbers has a different quantization, so it may be constrained to be even, for example. And the same thing happens in these other components, the 3.6, where some quantum number should be constrained to be multiples of 3 and so on. So this is an interesting fact. I'm not sure what this means, but this influences the spectrum that you can compute. Okay. So let me quickly talk about what happens in 8 dimensions and 9 dimensions, because what I say was in 7 dimensions, and I argued at some point that you can uplift these things to 8 dimensions and 9 dimensions, but I didn't justify this really. I can make that justification in 8 dimensions precisely because there is also a geometrical picture in 8 dimensions, which is given by F theory on a K3 manifold that now is elliptic. So you see that the moduli space is now given by gamma 2,18. This is dual to heterotic amplitude. The picture is very similar to a moduli space. Generically, you don't have any singularities in the thing, but when you go to the boundaries, this thing is an elliptic fibration. So you can have certain fibers that become singular. Again, the behavior of how these fibers become singular is encoded in the Euclidean sublattices of this time of gamma 2,18. These things were classified from the point of view of elliptic K3s in the mathematics a long time ago, and then in some recent work from the heterotic point of view, we found a match. there. And it is the same story. Here, as I said, the singularities, I told you that the lattices, when you go, these orthogonal complements, when you go to higher dimensions, they become larger. This corresponds to these frozen singularities that you can have now in 8 dimensions. There is only one kind of singularity. It's the D8 singularity. And it corresponds again in the orientifold picture to having a positively charged orientifold plane. You play this game of trading stacks and so on. Again, if you look at the 2D8 configuration, there are 2 inequivalent ones and there are these 2. So I call this lattices W and W prime. And again, you see that there is a difference at the level of these extra vectors that you have. And you can compute these orthogonal complements. So here I can justify it because the picture of frozen singularities had already been proposed by Witten in 98. So this thing is fine. But what about 9 dimensions? So in 9 dimensions, it's not clear because there is not a picture that you can say, oh, compactify this theorem, some whatever, and you can put frozen singularities there. It's not that clear. However, some time ago, there was a proposed geometrical picture of the type 1 prime string, where you take a K-tree, you make it elliptic, but you also make it real. So it means that the parameters that define your elliptic K-tree, say in a Weierstrass model, they are now real. If you treat this problem carefully, you will see that the modular space takes the form of the modular space of, say, the Hector string on a circle. So this game seems to work also in 9 dimensions, though it's even less well understood. But what I want to propose is that lifting that I showed you applies here as frozen singularities. This thing can develop AD singularities, and I say that if you have a singularity of type E8, you can freeze it. How? I don't know, but you should be able to do it. And also the 16 singularity. You should be able to freeze it. But this also comes in 2 versions, and it's the same thing as before. We have two different spaces. And this thing corresponds to the decompactification of that 2D8 and 44 and so on.
Sorry, can I ask
Yes.
you this question I should have asked earlier?
Yes.
You mod out by C2. This is C2 of spinner, right? There are 3 C2 that you can do.
Yes. So the precise statement is that this thing is the weight lattice of spin 32 mod set 2, and that means that you have the root lattice, and you also have a weight vector that corresponds to the spinor class.
But
It's
spin
It's not
32 spin 32 has a 2 center.
Yes, it's not the total, it's the other one.
Yeah, okay, so it's spin now for spin.
yes, yes, exactly. It's not a sort of
Okay.
it's
What
not.
about SO 32? Is it
Yes. SO groups are not realized. Let me see. The problem with SO32 is that the weight lattice is not even, it's odd, because the vector class is 1, 0, 0, 0, so this thing is an odd vector. That element is odd. So you cannot embed it into the Narayan lattice, for example. This means that at least in the Narayan component, you cannot get SO anything. So it's always a spin 32 mod set 2 and things like this. A group like SO3, for example, you cannot get it in 9 dimensions, 8, 7, it doesn't exist. So it's inconsistent with coupling to gravity. So yes, I never write it. So I never find any situation where I would like to write it, so because it doesn't show up.
Sorry for another annoying question.
No, it's
What about 432?
It's worse because then you have to quotient by set of square. Now the thing is not even an integral lattice. So but there is a problem here because we cannot apply the argument of ordering the O-planes to get these other theories from the orientifold point of view. Now these 2 arrangements are equivalent. This is something that you can check. In the 8-dimensional case, this is so this is even clearer in 9 dimensions because okay, you cannot find anything equivalent here. What does this mean? Yeah, there has to be a different mechanism that would produce the alternative vacua. Okay, and the answer to this is what I want to come to now. this has to do, when you construct an orientifold, it has to do with how you project the Ramon fields. So this leads us to discrete time. I suppose that just to I don't know if there are any other questions now before I move on. Okay. So this is another story. In principle, it does not depend on the picture of singularities, but the thing exists because of that prediction. But to understand what this is about, think of the type 1 string. You construct it in 10 dimensions from the type 2b, you mod out by the worldsheet parity. But this operation acts on the axiom by changing the sign, so you set it to 0. But recall that the C0 is periodic up to gauge symmetry. You have a gauge symmetry here. So you could also set C0 to 1/2. This would be consistent, okay? Because 1/2 is equivalent to -1/2. And this could, in principle, give you a new theory in 10 dimensions. This was a problem that was considered by SETI in 2013. It was not clear at that point if you could get a new theory. Very messy situation, but you can actually see that it doesn't. It brings you back to the same moduli space. It's the same theory, but a way to understand this qualitatively, and it will be useful for what I want to show.
Same moduli space and same observable. In principle, you have similar space, but it's still depend on.
Yes, I think I misspoke because moduli space, you're in 10 dimensions on so in this case, what are the moduli? Only the dilaton. So the theory, so you can in principle say that the massless level, this thing is equivalent. So this is, if you expect any difference, it would be at the level of massive states. But it turns out that they are exactly the same. And maybe I can convince you of this fact if I go to 9 dimensions and I dualize it to the type 1 prime. So this is the type 1 prime that we have been talking about. But now you only have two 08 minus branes, which is the standard component of the moduli space. You have your branes. So if you wanted to get the type 1 prime version of your new theory, you would have to turn on a discrete value for the integral of the C1 on the compactification circle. You would like to have this. And in this paper, Berkman et al. From 2013, they show that you can have a domain wall for theta, for this parameter, by taking a D8 brane and a D8 brane, you pair them. This gives you a domain wall. So it's this figure, I took it from the paper. But here you have branes. And if a brane intersects this domain wall, then you will have tachyons in the intersection, and this thing will be unstable. If you have the 8 branes, the thing is unstable, and the domain wall will decay. So the theories that were otherwise separated now, they actually live in the same moduli space.
So you mean a domain wall where theta would be 0 on one side and 1
yes, exactly. Exactly. So the trick here is that if you trade the stack of the orientifold with the branes, and you now take the positive orientifold, now you don't have branes. You don't need branes to cancel the tadpole. So the domain wall is stable now. And this is exactly what we were looking for, to have an equivalent theory for this one. And say, well, the new predictive theory is distinguished by the value of theta. This is the parameter that you need. And the discrete tangles do produce new string theories, maybe not in type 1, but in rank reduced components of the modular space, you can actually do this kind of thing. Now, in this moduli space, it does not only have this description of the 08 plus and 08 minus, it has two other descriptions when you do a kind of duality. I'll show it in a moment, but this is the picture of the moduli space. This is the original one. It was studied in this paper of Haroni and company. So this is the so-called double Parra background, and then you can do an duality, and you arrive at what is called the type 2D asymmetric orbifold. I will show you how they are constructed very briefly. But the point is that they also admit discrete theta angles. So first, consider this double Karpag background. It's very similar to the type 1. What you do is that you take the type 2b, you put it in a circle, and then you quotient by the worksheet parity. But this time you accompany that transformation with a half shift on the circle. It's similar to the CHL string picture that I showed. Since you have that shift, now you don't have fixed planes. There are no orientable planes, and there are no branes. So this tells you about the rank reduction. And here, usually, you would also set C0 equal to 0. And the duality of this theory with the OA plus or OA minus, you can think of it pictorially like this, like you have the two orientable planes, you do the duality, and then you get this thing, which in the literature is called a shift orientable plane sometimes. So how do you turn on the C0 here? It's very nice because you can implement this. So if you look at the action of omega on C0, as I said, it changes the sign. So you set it to 0. But here, if you put another transformation, so we are quotienting actually by transformations in the SL to set group of the type 2b. If you add to this thing a translation in the actual data, you get a transformation that the matrix is written there. This will fix the C0 to be equal to 1/2. And then you can see how this thing acts on the other fields of your theory. For example, the two-form fields, they transform like this. You have the doublet of the C2 and the B2. You multiply by this matrix. And the interesting thing is that this transformation is quite non-trivial. You can construct a combination of these two fields that is actually invariant under this transformation. It takes this form, B2 plus 2C2. And in the 9-dimensional theory, this invariant two form will play the role of the two form. Okay? Then you can consider what happens to branes. So if you take a D1 brane, it's better to look at this picture. So in terms of PQ strings, a D1 brane is a 0-1, but that brane is not invariant in this transformation. Actually, it changes to this. So from here you can see that these two PQ strings, they are mutually BPS. So when you take the quotient, you will get a string that is non-BPS. So you can also see it from the point of view of how this object is charged under the fields. Here I have the usual expression for the charges of the PQ strings under the two-form fields. You can rewrite it in this way. And this D1 brane will have a charge with respect to the B2 field. And it will have a charge with respect to the C2 tilde. This could not possibly be a BPS string. So in particular, the charge of this thing with respect to this form is 1/2. You set Q equal to 1 to get this. Okay. But you also have a PQ string that is invariant under that transformation, and this will give you a BPS string. This will be your fundamental string in your 9-dimensional theory. And if you compute the charge of this thing with respect to Q, it's 1, because Q is equal to 2. And what you see is that if you look at the possible charges that strings can have, some of them can have well, charge 1/2, but this, if you think of a lattice of string charges, those sides in the lattice are not populated by BPS strings. This means that the spectrum of strings is not BPS complete. Now, why is this important? You could say that this is the distinguishing feature of these theories. Every other theory that we already had a BPS complete spectrum. And for that reason, it was assumed in some papers of Swampland that, okay, this is a pattern. If I can always assume that I have a BPS, that I can always have BPS completeness for my strings. And use this assumption to try to reconstruct the landscape of string theory.
What do you mean by BPS complete?
Yes, so there are allowed charges for the strings that are not populated by BPS strings. In general, the spectrum is complete in the sense that for any charge that you want, you have string, but some of them are not BPS. Yeah. And in this case, it's, the BPS lattice would be of index 2. So, okay, so there are some non-trivial things that can happen even if you have so much supersymmetry. Okay, so the AOB theory is similar to the Parra. Instead of using the omega transformation, you use -1 to BFL, which is also in the SL2 set group. And you have the standard construction, but you can also put a translation in the axodilaton, and you get an alternative version that will turn on a discrete theta angle. Now, usually the duality transformation that you do between the AOB and the double Parra is GS goes to 1 over GS. Here there is a factor of 2 that appears, and so the correct transformation that you have to apply is GS goes to 2 over GS. Other than that, if you construct the moduli space of this theory, it looks very similar to the original one, but you can see that, okay, so here this moduli space, you have only two moduli, these are Riemann theories in 9 dimensions. So this is the measure of the radius in the type 1 prime setting and the string coupling. And you can see how this thing goes up, because now the self-ball point is at 2 and not at 1.
So what are the boundaries between the various regions in this figure?
Okay, so this boundary here, you can see that it relates the theory to itself. So that's the symmetry. And here you have enhancement of gauge symmetry, what you have SU2. The other ones are just boundaries between two different theories. So when you move here, you have to change your description. And at this point, you have an identity between the couplings and the radii. Fine. So then you would like to know what happens in 7 dimensions. Can you repeat this analysis? So as I said, you can take a theory and put it on manifolds like this to get this rank reduced components, and you can turn theta angles here. This is only when n is equal to 2, 3, or 4. There is another possibility, which is n equal to 6, but that one does not admit a discrete theta angle. This is in line with the predictions that are made from process similarity picture. Now, if you want to do the analysis of theta angles, it's better to look at it from the point of view of the type 2b underlines theory. And you compatified it on a so-called Beaver-Bach manifold. So a Beaver-Bach manifold is very simple. You just take a torus and you quotient it by the isometric group that will preserve its flatness, let's say. And it's very interesting that these kind of compatifications were not considered. If you were to systematically look at compatifications of strings on Beaver-Bach manifolds in this setting, you would obtain these different theories, but it was not done for some reason.
It's a quotient without this point.
Yes.
So,
the way in which you construct this background, this geometry, is compatible with turning on values of these quantities. These are now the quantities that play the role of theta angles. So you integrate the C2 and the B2 on a T2. That T2 is a special torus. So here you have a D4 times S1, and this is a background for a theory, so there is an analytic fiber. So the Beaver manifold is more like T2 times S1, some quotient. And that T2 is where you turn on these fields. There are some values that you can have, and they correspond to these alternative theories. For example, when n is equal to 3, you can have this configuration. It will be fixed under the corresponding transformation. And for n equal 4, you have a similar story. But for n equal 6, you cannot do it. So this is very nice. We recover, we find what we should have found from the M theory picture. You can also do an analysis of the spectrum of strings, and you will find that it's not BPS complete. So one last thing, just to say, these are the gauge symmetries that you find in these components. And here I wanted to show you how they are altered when you turn on the discrete angle. It's not very interesting because in the case of the of the set 2 background, you do see a difference in the topology. By the way, this index here is related. It gives you the current algebra level for the string worship. But here in the set 2, you do get a difference between the topologies, but then you don't see that difference in the other components. But the reason is that they are rank 1. So the only thing that you can have is SU2. The other thing that you could have, if you would have a non-trivial topology, is SO3. But SO3, it doesn't show up ever here. So these things are indistinguishable. If you want to see a difference in the topologies, you have to compactify further on circles on Torah. And so, for example, if you are in 6 dimensions, you can realize in this component an SU3 mod set 2. And when you turn on the theta angle, it will give you an SU3. So it kills massive states. So it's the picture works, but it's not that visible from the 7-dimensional point of view. And the thing with the levels, well, one comment is that this level 2 can be, you can do this string theory computations and you find that the level is 2. But this is in another work with another Freiman, which is more recent. We did an analysis of the possible gauge symmetries you can have in a variety of moduli spaces. This is in 6 dimensions, and we can get the rules for computing these things also from the lattices on. So there is a match there, which is very nice.
What determines the level here?
Sorry?
What determines the level?
What determines the level?
Yeah.
Yes, so you can in principle get the level if you look at how the gauge symmetry realizes the current algebra in the worksheet, and then you just look at the OPEs and you see what is the level. The way in which you can compute the levels more efficiently, you see that no, because the F theory is dual to another string theory that has a worksheet description, so the level is invariant. For example, another thing that you would like to do is you compactify these to 2 dimensions, and then there is definitely a worksheet picture where you will compute these levels, and then you can just go back to 7 dimensions if you want. So it's consistent with
SQ3 mod C2.
Yeah, so you have the root lattice, and then sorry, this is set 2, A2, set 2, maybe it's set.
Set 3.
Maybe it's set 3, yes, and maybe a typo. Yeah, that's true. Thank you. Yes.
Could you explain again the current algebra level? How do you see this from string theory?
Yes, so in the paper with Miguel Montero, where we discussed these discrete theta angles, the arguments that are used to see the level are more from the point of view of space-time. But maybe one quick way to see it is that, so you are in 9 dimensions and you have SU2 and you want to know what is the level. Now there is a bound on the central charge of the string worksheet. If you take the string worksheet to have central charge 12 on the left moving, the level that you set for the SU2, it may violate this bound because it will contribute to the central charge differently. If you set it equal to 2, you will saturate it exactly. So this is a heuristic way of seeing it. You can also see it from the point of view of space-time physics. Using the Bianchi identity, there are some other arguments that are in the paper, but I don't have it in my head right now. Okay.
So, but it's not like CHL type construction where you just directly see the level from CFT.
Yes, in particular, these theories don't have a heterotic string realization, so it's not as straightforward. But as I said, if you compactify to 2 dimensions, you do have some internal CFT that you can is under control, is in the literature, and the levels match as they should. Yes, so to finish, so these are maybe the 3 most important messages, at least in my opinion. What I find amazing is that from this point of view of forcing singularities, you can encode every moduli space from 7 to 9 dimensions. And these things are not well understood, but they are useful. The other thing is that discrete attendants can yield new string theories. Okay. And the difference is at the massive level. And the other point is that theories of quantum gravity, which is in supercharges, they can have an incomplete BPS string spectrum. So we learned these things, I think.
Can you say again what you mean by the incomplete BPS spectrum?
So you have your theory, you will have some allowed charges for the strings. Okay? In particular, it can be 1/2 for the 2-from. Then you ask, well, is there a string that has charge 1/2 that is BPS? And the answer is that there isn't. And
so this does not contradict completeness.
No, because there is a non-BPS grain that gives you the. It's like, I think of the type 1 string where you need a spinor for the spin 32 mod set 2, and that is a non-BPS D0 grain. So the spectrum is completed in that sense. Other things to do, well, I think it would be very interesting to look at compactifications on Biberback manifolds, like these flat manifolds in lower dimensions. That you may find other things that I don't know. So it's something that I would like to do in the future.
You don't have a classification for higher dimensional manifolds, right?
Well, I think that these things are classified. No, you mean the Biberbacks?
Biberbacks.
Yeah, I think they're classified to 5 or 6.
A lot more. So you cannot just take 7D manifold and use it.
Yes. I don't know, but I think these things you can kind of control them using some software like Karat. So it may just get out of control.
This is matched by classification of all. It's 1-to-1. But again, you don't have classification of all the poles either.
Yes, right. But you mean minimal supersymmetry? Yes.
No, this might be equal to H. This is not me.
But then equal to, yes. And how many supercharges?
Just comparing the orbital classification, where you see more supersymmetry, that's where you get the bigger one. After all, they are flat.
Yes. Yes. Yeah, in general, the classification of these moduli spaces is an open problem, so it's good to. Yes, just. Of course, it would be nice to do a worksheet analysis of these things. We didn't do it in the paper, though it should be a different worksheet because you're quotiented by different symmetries. And for me personally, I would like to understand better what is this process singularity thing, which it holds, it exists in other settings like 6 dimensions with minimal supersymmetry. It was explored in a paper recently, kind of. So yeah, I think this is something that it's worth doing. So thank you.
No questions? Yeah, well, I'm not sure I got a big table of all string vector we can have equal 7 this way, but let me try to see if I understood somehow the idea that you can start from the classical one, and if you move in moduli space and cross one point where things are singular, then there are new open space of moduli space behind the singularity that are not the classical vector, but everything is connected in that way to the standard field.
So yes, I don't have a table, but maybe I can go back here to the picture. Sorry, here. So the big picture is that you have 10, a priori you have 10 moduli spaces, 6 and 4. And for these 4 here, when the values are 2, 3, and 4, there exist in equivalent versions. So the story for this thing is untouched. For the heterotic string, there's nothing going on. And you can say that here there are domain walls in the moduli space which you can cross, and this will turn on the value of the theta angle, and this is an inequivalent theory. So, but I think the big picture is that you have 10 components of the moduli space. There are actually 3 more. and these three are related by discrete parameter with other three. So these things are like.
Can you encode your discrete parameter eventually so to the C3?
I don't think so. No, I don't think you can, because for the two moduli spaces that are related, the value of the tree form is the same.
So how does clearly the value is not as it's flat, but how does M theory know in which two versions it will end up?
It knows because the lattice that is associated to the singularity, it has roots, and those roots give you the AD singularities. But the other vectors also have geometric information. So this is easier to explain in F theory, because in F theory, this set 2 that I write is related to the so-called model variable of the K tree. So you have a group of sections, you have the K tree, you have the sections, some sections are torsional. So when you freeze two singularities versus the other two, in one configuration, you can say that a section in the K tree is frozen, and in the other case, it is not. So there is some difference in the geometry between these two constructions. It knows in that sense.
Is there any question online? So let's